Thank you, Vladimir, and it's great to be here, even though we are masked, but at least I can take it off. Okay, so today I'm going to talk about what we call network archaeology. I will explain what it is, and I will present a couple of results and a few questions about this area. This is a kind of new area, and I find it very exciting and nice to play with. So if you like some of the problems, you're welcome to work on them. And on Wednesday, I will talk about something completely different. So this is the results I will present are based on joint work. Well, in the first half, it will be a joint work with Sebastian Wübeck and Luc Devroy, and in the second half, it's joint work with Luigi Adario Berri, Luc Devroy, and Vasiliki Veluna. Okay, so what is network archaeology? So these are statistical problems that occur when we look at a huge network that has been growing in time, and we want to say something about the past of this network. Right? So we know that this network has been growing. You can think about spreading of rumors, spreading of viruses. You can think about social networks, whatever. There are many exampmples. There will be no examples. This is only a mathematical talk, but you can imagine examples where you have a network that grows in time, and after a long time, we have this gigantic network. We look at it, and I want to say something about how did all of this happen. So who was patient zero, or where did the rumor start, or if the nodes that are influential today, have they been influential always in the past, and so on and so on. Okay, so I will formulate a few very concrete questions, and then we will play around that. Okay. But this is the general theme. This is what we call network archaeology. Okay, and there are a few examples. This is not a big field, but as you will see, there are some nice mathematical problems here. Okay, so these growing networks are often modeled. But when we want to deal with them mathematically, then you need some kind of a model, and there are the typical models are based on some simple growing dynamics. Okay, some simple local rules that govern how the network grows, and that's what you can think about preferential attachment, for example. Right? These are the typical kind of models that are used to model big social networks. That when a new node arrives to the network, it attaches to some existing nodes according to some simple rule. This rule can be, for example, you attach to vertices with probability that's proportional to the degree, to the connectedness of that node. Okay, so these are the kind of simple rules of growth dynamics that describe these models. Okay. So in this talk, mostly I will talk about the simplest possible networks, and it's kind of exaggeration to call them networks. These are trees. Okay, so the simplest networks are just trees. And the very simplest of these growing, randomly growing trees is the uniform attachment tree. Okay, so when a new vertex arrives, so vertices arrive one by one, and when a new vertex arrives, it just chooses one vertex to connect to, uniformly at random. Okay, this is the uniform attachment rule. If the new vertex that arrives attaches to an existing vertex, not uniformly and random, but for example, as some function of the degree of the vertices, then we call this preferential attachment trees. Okay, so in most of the talk, I will talk about just trees, all right? And mostly uniform attachment and preferential attachment trees. I will give you the precise definitions in a second. Okay. All right. So the uniform attachment tree, this has been studied in in probabilistic combinatorics a lot. These are called the uniform random recursive tree. And even preferential attachment trees had been studied before they became fashionable in modeling social networks. The simplest of them is called the plane-oriented random recursive tree, for reasons I'm not going to explain here. But anyways, these objects had been well known for a long time, and lots of things are known about them. So we know the degree distribution, asymptotic. We know the diameter of these. We know lots of things about what these trees, these random trees, look like. Okay. So here's the first problem that I will talk about. We call this the finding Adam problem. Okay. So Adam is the origin of the network. Okay. So we have a growing network. Let me just draw a little picture here, if I find it. Chalk. Oh, here. Okay, so let's say in the uniform attachment tree, this is Adam, the vertex number 1. Okay, and then this Eve comes, number 2, and it has no choice. It will attach to this one. And now vertex number 3 comes, and now it chooses one in the uniform attachment model, one of the existing vertices uniformly at random, and it attaches to it. Okay, number 4 comes. And now it chooses one uniformly at random and attaches to it, okay? And so on. 5 and attaches to it. And we grow this network for a long time, and then we observe the tree, but without these labels. We don't see these labels. So what we observe is this tree. And then now I'm asking you to find Adam, okay? Which is vertex number 1. Where did the whole thing start? Okay, this is the so-called finding Adam problem. Now, in order to formulate this, it's clear that that number 1 and number 2, Adam and Eve, are indistinguishable, right? Because after day 1, this is the network, and from then on, they play exactly the same rule. Okay, so we cannot expect to find the vertex with high probability. At least the error must be 50%. Okay, because these two vertices are indistinguishable. So in order to formulate the question that makes a little bit more sense, what we ask is that when we observe this network, we are allowed to choose a few candidate vertices. Okay, let's say k of them. Okay, but so we can select in any way we like k candidates, and we want to make sure that the Adam, vertex number 1, is one of these k with high probability. Okay, so let's say if we allow a probability that's probability of error that's epsilon, then what we want is to select a set of size k, okay, such that the probability that the root vertex is among these k vertices is at least 1 minus epsilon. And now the question is, how large does this k have to be? Okay. So this k depends on epsilon and depends on n, right? N is the size of the network, all right? So this is the first question, the finding Adam question. How large does this, how many vertices do we have to choose in order to make sure that with probability 99%, vertex number 1 will be one of those k vertices, okay? Is this clear? All right. So this is what a uniform attachment tree looks like on 50,000 vertices. Okay? So now I'm asking you, can you please find which is vertex number 1? Okay? So that's the question. All right? How many vertices do we have to output to make sure that with probability 99% the right vertex is there? Okay? This picture is not mine. This was stolen from the website of Igor Korchemsky with his permission. Okay. So the main results in this this paper is now a few years old. The main results were that this k, maybe surprisingly, is independent of the size of the network. Okay? So we can find just a constant number of points of candidates, independent. Only depends on the probability of error that we allow, but it doesn't depend on how large the network is. It can be 50,000 or 500 million. we have a constant number of, we can find a constant number of vertices that guarantee that with probability 99%, the Adam vertex number 1 is among them. Okay? And that was maybe a nice little surprise. It's not that surprising if you think about the problem. Maybe a little bit more surprising was that finding vertex number 1 in a uniform attachment tree is easier than in a preferential attachment tree. And this was surprising for us intuitively because you may think that in a preferential attachment tree, you see old vertices tend to have high degrees, right? So because and they keep attracting vertices more, but provably this is actually a harder model, and I will explain why. Okay. All right. So how do we attack this problem? Maybe the first idea is that old vertices have a long time to attract more connections. So let's just look at the degrees. The degree is just the number of connections of a vertex. Okay. And so for example, the root vertex, Adam, right? What's the degree? Well, at time 1, it has 1 connection. At time 2, it has 1 plus 1/2 on expectation, and plus 1/3, and so on. So the expected degree is about log n, and this is well concentrated. There are central limit theorems, so we understand very well what the root degree is. Okay. However, it's also well known that in these uniform random recursive trees, the degree of highest vertex has a much higher degree. It's not ln n, it's log base 2 of n. So it's a constant factor larger. Okay? So in fact, the degree, the vertex of highest degree is far away from the root. So there's this recent nice paper by Laura Eslava. She proved that that in fact the distance of the highest degree vertex from the root is c log n. Log n also is the diameter of the trees is a constant times log n. So it's really far. Okay? So sorting by degrees is not going to work in uniform attachment trees. Okay? So we have to come up with something else. All right? So here's a really simple method, and this is based on that works. This is based on a very simple notion of centrality. Okay? So in this picture, you see for each vertex, for each candidate vertex, we will look at, we will try to measure how central that vertex is. Okay, and one way of measuring it for any vertex, these are the connections, and now we can look at how big these trees are that hang off that vertex. Okay. And we will say that this vertex is the most central if the largest subtree that hangs off, the largest of these subtrees, has minimal size. Okay. Right? So if we have a leaf, right? A leaf is just a vertex of degree 1. If you have a leaf, then it has only one tree, and that it has size n-1. Okay. But in every tree, this is an easy little exercise. There exists 1 or 2 vertices that have the property that all these subtrees have size at most n-1/2. Okay? These are called the centroids of the tree. Every tree has either 1 or 2 centroids. Okay? So let's do that. Let's sort vertices according to this measure of centrality, which after writing this paper, years after we found out, this is called the Jordan centrality. So if we sort these vertices by their Jordan centrality, then if k is essentially 1 over epsilon, like log 1 over epsilon, then the k most central vertices will contain the root with probability 1 minus epsilon. Okay? And I'm not going to show you the proof. This is based on really simple Poillaran Poirier arguments, because you see, if you look at the root here, all these subtrees that hang off here, so this is the root vertex, these behave like a Poirier, right? Because now, when a new vertex comes, it will just choose one of these at random, and we will place that ball into that bin. Okay? So this is the way these subtrees grows are described exactly by a Poirier, and then you can work it out. Okay? Because we know the limit distributions and everything. Okay? So this is nice. This is the first method that shows that you see K doesn't depend on the size of the network. K is at least something like 1 over epsilon. And it's easy to see that you cannot improve on this because the root remains a vertex. Sorry, the root remains a leaf vertex with probability 1 over, if the tree has size K, then with probability 1 over K, the root is still a leaf. Okay? So if we are to, you see, if you look at the big tree, the problem only becomes easier if you only look at what happens after, if you can observe the first K vertices, and if at that time the root is still a vertex, then it has the root is still a leaf, then it has the worst centrality of all of them. Okay? So it's easy to see that you cannot do better than 1 over epsilon with this method. Okay? With looking at Jordan centrality, it's simply because there's a certain probability that nobody will attach to the root vertex except for vertex number 2. Okay, for K steps. All right. But this is an easily computable statistic, and so it's quite convenient. It's good to think about it. Okay, but is this optimal? Well, we can think about what is the optimal rule. Okay, this is a statistical classification problem, right? Or we want to find which vertex is most likely to be the root, and there is a maximum likelihood estimator, right? So and the way this works is for any tree, if you observe a tree, right, without labels, we observe something like this. Then what we can do is that for every vertex, we can imagine that if this was the root, okay, how likely is this vertex to be a root? So what are the restrictions on the labelings? Well, the only restriction is that on every path, the labels must be monotonically increasing, right? So these are called recursive trees. Right? When on every path starting from the root, the labels are monotonically increasing. Okay. So now we can just count how many there are, how many such recursive labelings there are. Okay. And the maximum likelihood estimator is just the one that maximizes the number of such labelings. Okay. And this is the expression for the likelihood function. So what this TUV down arrow means is that if we imagine that this vertex U is the so we're trying to calculate now the likelihood of this vertex. Okay. Now for every other vertex V. Now we look at the size of the subtree that hangs off V, that's away from U. Okay? And we take the product of all of these over all vertices. Okay? Times there's a factor which is really annoying that counts automorphisms. Okay, I'm not going to define it, but essentially, if you ignore that factor of that automorphism factors, then for every vertex we look at the size of the tree, and we take the product of them over all vertices. Okay, so U is fixed, that's our candidate vertex. And now for every other vertex, we compute the size of this tree, and then we take the product. That is the likelihood function. Okay? All right, so once we have this, well, now we know what the optimal rule is, the optimal rule for finding the root vertexes. Analyzing this is not so easy, okay? But we can prove lower bounds. So a really simple lower bound is that if k is smaller than something like e to the square root of log 1 over delta, then no method can work. Okay? This is surely not optimal, but that's the best we have right now. And this is the proof. Essentially, this kind of configuration that the tree looks like this: a long path, a path of length, let's say 10 log k, and then a normal-looking random recursive tree. This happens with certain probability. Okay? And if this happens, then that vertex number 1 is the worst according to this the likelihood function among these vertices. Okay? And this happens with this probability. If you have k vertices, that's something like e to the minus log k squared. And if k is what we have here, then this is bigger than epsilon. Okay? So it's a really simple construction. We don't have anything better. This is the best lower bound we have. Now, can we do better than that 1 over epsilon? Of course, this is much. This guy is much smaller than 1 over epsilon. It's e to the root log 1 over epsilon. Okay. So can we do better? Well, what we did was we just ignored that annoying automorphism factor. Okay? And we looked at the rule that just minimizes this centrality measure that I explained, right? So for every vertex, the centrality is computed by taking the product over all other vertices of the size of the subtree that looks away from that vertex, okay? Ignoring the automorphism factor. And this measure of centrality actually appears in earlier work in a slightly different context, in a paper of Schach and Zaman. They call this rumor centrality. So they were looking at finding the origin of rumors in rumor spreading. Now, interestingly, just last year, this really nice paper of Harry Crane and Xu came out, and they proved that, in fact, what we did was the right thing. You can ignore that automorphism factor, and the ordering of the vertices is exactly the same. So these two are actually the same rule, which was kind of surprising. So ignoring that automorphism factor, which we did because we couldn't do anything better, that is actually the right thing to do. This implements the maximum likelihood ordering. Okay, and then we analyzed this, and when we proved that if k is at least e to the log 1 over epsilon over log 1 over epsilon, then this method works. Which is nice because this k is now smaller than any power of epsilon. Okay? It's still far away from the lower bound where in the exponent we had the square root of log 1 over epsilon, but here we have log 1 over epsilon over log 1 over epsilon. All right. Now, what about preferential attachment? You can look at our first really simple method where we looked at just the subtree sizes, and that works whenever k is 1 over epsilon squared, a little bit better than 1 over epsilon squared. Sorry, a little bit smaller. If k is a little bit bigger than 1 over epsilon squared, then this will work. Okay, we proved a burst power first, and I think we had e to epsilon to the minus 4, but Banerjee and Bamidis showed that actually it's close to 2. Okay, which is much larger than the 1 over epsilon that we had for the uniform attachment tree. Okay? So for preferential attachment, remember in preferential attachment, what happens, the way the network is Chrome, maybe I didn't explain this very well. So we start with Adam and Eve, and now when a new vertex comes, then the probability of attaching to here is twice as large as the probability of attaching here, because this has degree 2 and this guy has degree 1. Okay? So this is more likely to attach here. And now the probability of attaching here is 3 times more likely than attaching here. Okay? But maybe we will have this one. And now the probability of attaching, this is 3, 2, 1, 1. Okay? So this is the preferential attachment mechanism. And so here, the simple Jordan centrality method only gives us 1 over epsilon squared. So this k has to be much larger, quadratically larger than in the uniform attachment tree. Okay? And the reason is that you see, the probability that the root remains a leaf for a long time is much bigger, right? Because if for at the beginning, vertex number 3 has 50% chance of attaching here or 50% chance of attaching, but if it attaches here, then now the root is in trouble. Okay? Because then the next guy will be more likely to attach to here, and now the root is in even bigger trouble. So if you work it out, then you see that the probability that after k steps the root is still a leaf is not 1 over k, it's 1 over square root of k. So it's much bigger, yes?
You started to say that the 2 first vertices were indistinguishable.
Yes.
So why don't you say that both of them are roots in some sense?
We can say that, yes.
And this argument that made is not true anymore. That if you say either 1 or 2 are roots.
Sure, but again, that's fine. It's still, we have still the same problem, because let's say if 3 attaches here, but 4 now attaches here, then all of a sudden, okay. So it can happen that something goes wrong at the beginning, and then it's difficult to recover. Okay, so that's what may happen in preferential attachment. Okay. So, and then here this picture shows that in fact, for preferential attachment, we cannot hope for anything better than 1 over epsilon. Okay, and the reason is that this after if n is 1 over epsilon squared, okay, then this configuration happens with probability epsilon. So what is this configuration? That the root is still a leaf, and vertex number 2 has square root of n neighbors, 1 over epsilon neighbors, that are, all of them are leaves. That means that the root and all of these guys are indistinguishable. So there's no way of telling them apart. Okay? So this means that for a preferential attachment network, preferential attachment tree, no rule can do better than 1 over epsilon. But for uniform attachment, we could do strictly better than any power of epsilon, right? Remember, we had this e to the log 1 over epsilon divided by log 1 over epsilon, which is better. So this is our surprise that preferential attachment is provably harder, even though the upper and lower bounds don't match in any of these cases, but the lower bound for preferential attachment is bigger than the upper bound for uniform attachment. So this is the summary of what I just showed you. So the optimal value of k for uniform attachment is between those 2 values. So it is sub-polynomial. We don't know exactly. I think the upper bound is probably the right one, if I have to guess, because the lower bound is just silly. And for uniform attachment, I don't know. Sorry, for preferential attachment, I'm not sure where the truth is. Probably 1 over epsilon squared, but there are some open problems. Okay, so that was the first half of this talk. there are some references here. Since this talk is recorded, you can just go back and pause the video to read. So Shah and Zaman, the paper I already mentioned, they looked at not this type of model, but a kind of diffusion model. So you can take an infinite ternary tree or infinite DRE tree, and then now you place vertex number 1 somewhere, and now it grows in a diffusion manner. Okay. So that was the model. You can ask the same kind of questions. Paul Inglow and Varun Jok showed that this really nice result. And the central node, let's say for uniform attachment, the node that is the centroid, after a random time will remain the same forever. Okay, which is really nice. This is called the persistence of centrality. And Banerjee and Bamidi I already mentioned. They have a couple of really nice papers on it. Okay, there's a version of the problem when you don't start with a vertex, but you start with a little tree. Okay, that's the seed. Okay. And now you want to find the seed. Like we know that internet didn't start randomly, it started with a small network in the military. Okay? So now you want to find that one. And here, let me just go continue here. So the second problem is what's called the broadcasting problem. So here we have again a uniform or a preferential attachment tree, but now the vertices have colors. Okay, the root vertex has some random color. Let's say blue or red with probability 1/2. Okay, and now the way broadcasting works is that every neighbor will take the same color as the root with probability 1 minus q. So with probability 1 minus q, this will be still red, but with probability q, the color flips. Okay. So these are the good children that preserve the color of the parent, and the rebellious ones, they change the color. Okay. The parents are Republicans, they become Democrats, or vice versa. Okay. So this is the way broadcasting goes in the tree. Okay, so Q is the probability of flipping, and now the classification problem is that I show you the tree with the colors but without the labels. So I'm not telling you which one is the root, of course. I show you this color tree, and I'm asking you what's the color. Can you tell me what the color of the origin was? Okay. And what is the optimal probability of error? Okay, that again depends on the size of the network, and depends on this flipping probability Q. So we denote this by R star. Okay, so how does this depend on N and Q? Okay, now maybe it's not surprising anymore that it doesn't depend on N. So the real question is, how does it depend on Q? So this is how the network is grown, right? So this is the root here. It's blue in this case. Number 2 was a good child. Number 3 was a good child of 2, right? Number 4, where's number 4? Number 4, oh, it's a rebellious one, right? It flipped color from its parent who was blue. Now it became red, and so on and so on. But now what you observe is just this tree. Okay, so this is what I show you. And now I'm asking you, what's the color of the root? Of course, we don't know what the root is. Can you tell me what it is? A more difficult variant is that I'm only showing you the color of the leaves. Okay, and this is what this is the. So the broadcasting problem is typically was studied for regular trees, like this. Let's say a 3-ary regular tree, right? And now after k levels, I show you what the values of the leaves, the colors of the leaves here, And now I'm asking you what was the color here. Okay? So this problem has been studied a lot. This is the version of it for these random recursive trees. I show you the colors of the leaves, and I'm asking you what's the color of the root. Okay? All right. And this is in this paper with Luigi, Luc, and Vasiliki. Okay? Now, first of all, trivial lower bound is Q half, right? Because with probability Q, Eve changes the color of, Eve is rebellious, changes the color of Adam, and now we don't know. Because Adam and Eve are indistinguishable in this network, so the best we can do is random guess. So Q half is a completely trivial lower bound for which holds for all n. Okay. We know what the optimal classifier is, right? Because we know the likelihood of each vertex to be the root. Right? We calculated that before. That's this function, right? And so we can just sum the likelihood value for all blue vertices and for all red vertices, and we compare. This is the optimal rule. Now, good luck with analyzing this, but at least we know what we have, what the optimum is. All right. So of course, the first idea, especially if you listen to the first half of the talk, is to try to find the root. Because we know how to find the root, at least we know how to output a small set of constant size, k of epsilon, that contains the rule with high probability. So let's say we find these k candidates and we take a majority vote. Right? That's the first. And then the probability of error is essentially, well, epsilon, right? Epsilon is the probability that our k vertices don't contain the root, so then there's not much we can do, and the probability that the majority is wrong is upper bounded by the probability that this set is not monochromatic. There's at least one change in this set, and this is actually not a bad. It sounds like a silly upper bound, but this is kind of the right one in this setting. So we get epsilon plus q times k of epsilon. When the upper bound this is like a first moment kind of upper bound, and then we can optimize in epsilon, and we get that the probability of error is bounded by a constant only depending on q. It doesn't depend on n, and we get q to the 1 over log 1 over q. It almost matches that trivial lower bound that was q. Right? This is just a little bit worse than linear. It's q to the power of 1 over log 1 over q. And the preferential attachment is kind of bad. It's q to the 1/4. It's still far away from the q half lower bound. Okay? All right. But can we do better? Well, of course we can, because it turns out that what matters when we want to find the color of the root is not the number of vertices that we find, but if we can find a vertex that is close to the root, that should work really well, right? So in particular, if we could find something that is within constant distance of the root, then the probability of error will be only proportional to q, right? So the probability of error, right? If we find a vertex here, right, then you can compute exactly what is the probability that this guy is wrong, right? It's what's there, right? What you need is that the number of flips on this path is an even number. Sorry, is an even number, and then you won't make an error, right? And that you can upper bound by q times the distance. All right. So can we find a vertex that's close to the root? Okay, and the only thing that matters is the expected distance. All right. Okay, so here's a proposal. Let's look at the centroid of the tree. Okay. We feel that the centroid might be close to the root. And in fact, we could prove that the centroid is within constant distance of the root. And then we found this nice old paper that shows that, in fact, the centroid is within distance 1 of the root. Okay. Well, there can be 2 centroids. So this is for the closer centroid, right? So there's either 1 centroid or 2 centroids. But anyways, and for preferential attachment trees, one can also prove this. Just to give you a feel of why this is true, not the one, but why the centroid is within a constant distance of the root. So this is the root vertex. Now, if the centroid is far away, right? This VT now is the centroid. So if the centroid was far away, then it had to happen that if I look at this subtree and this subtree, then this subtree must have more vertices, right? Then this subtree has to have at least n-half vertices because that's the definition of the centroid. But for that to happen, we must have that we have 2 urns at the beginning. Urn number 1 has T balls. Right? So this says that if the centroid is at distance t, then this urn has t balls. This urn has only 1 ball, and then this urn has to catch up with it. But that has a really small probability. It's exponentially small in t. Okay. So with this, we can prove that in fact the distance of the centroid to the root is bounded by an exponential random variable. Okay. We don't really need that because only the expected distance matters, and then that's one. So what we get is this really nice bound for the uniform attachment model that the optimal probability of error is bounded by Q. That silly lower bound, the Q half, is essentially correct. That you can improve that constant a little bit, but we don't know what the exact constant. Okay. So you can improve that constant in the lower bound a little bit. I don't know what the right one is. Okay, and moreover, this probability of error is smaller than 1/2 whenever Q is smaller than or equal to 1/2. Okay, and similar bounds hold also for preferential attachment. Now, in the more difficult, this was of course for the centroid doesn't have to be a leaf, right? So this method only works if we observe the colors of every vertex. Okay? If we only observe the colors of the leaves, then we still have a constant times Q as an upper bound, and here this is simply follows from the fact that there will be leaves close to the root. Okay. So what you can do is find the centroid, find the nearest leaf to the centroid, and we know that the centroid is close to the roof. There are leaves close to the roof, to the root, and therefore the distance will be small between the centroid, between this leaf vertex and the root. Okay. So we get this constant times Q upper bound, and also you can show that the probability of error is strictly smaller than 1/2. So we can do strictly better than random guessing whenever Q is smaller than 1/2. Okay. All right. You may wonder that what happens to the rule that simply counts colors. Okay? We just observe this big network. We just count how many red and how many blue vertices there are. And it turns out that this also works if Q is small enough. Okay? In particular, if Q is smaller than 1/4, then this will work in the sense that it will be better than random guessing, strictly better than random guessing. And moreover, the probability of error is bounded by a constant times Q. Okay? So for small Q, this works really well. If Q is bigger than 1/4, then it dies. Then this method cannot tell. This is again by simple urn arguments. You can see that when the probability of flipping is bigger than 1/4, then counting colors is not going to work. But this other method, the centroid method, that works all the way up to 1/2, q equals 1/2. Okay, and then now this is a little bit kind of fun. Can be characterized for what values of q can we do strictly better than random guessing? Okay, so I say strictly better if the probability of error converges to something which is smaller than 1/2, or the limb sup of this is smaller than 1/2. Well, this happens always in the model where we observe all vertices. This is always possible except when q equals 1. If q equals 1, then it's very easy to see that, you know, then these colors will just simply alternate, and you can't tell them apart. Adam and Eve have different colors, and then you just can't tell them apart. Okay? But even if q is bigger than 1/2, but strictly less than 1, we can do it. That was kind of a difficult construction, but there is a rule where that works. Whereas if only the leaf colors are available, then again you can do strictly better than 1/2, except when q is 1 or 1/2. If q is 1/2, then that means that every vertex has a random color, and but the root is not a leaf with very high probability. Okay, so we don't know. So if q equals 1/2, if we only observe the leaves, then there's nothing we can do. But if q is bigger than 1/2, then we can do something again. So this is q bigger than 1/2 is maybe not. It's just fun. It's not a very important problem. Yeah. Well, we know that the maximum likelihood falls somewhere in between those two, but we don't know how to analyze that. Yeah. So it must be at most q, and at least q half. But yeah, I don't know. Yeah.
Do I assume q to be known? Yeah or no?
Yeah, q is known. Q is known, but it's not difficult to estimate it. So yeah, I think that shouldn't be hard. Yeah. Oh, the question was if q can depend on n. That's very nice. I don't know. That's a different ballgame. Yeah. I guess the problem becomes when q goes to 1/2 in some non-trivial manner, and then there can be problems. Most of the things that the tools are non-asymptotic, so you can just plug it in and see what happens. But we haven't done it. Okay. So in the last few minutes, I will just say a few possible extensions. These are the questions I promised. So you can look at other trees. Okay. So for example, a fun kind of type of tree is when attachment is not uniform anymore, but it depends on on time. So it's somehow older vertices get forgotten, right? Nobody cares about Madonna anymore in social networks, right? She's old, but the new ones, Cardi B has just come, so you're more likely to connect to Cardi B, right? So now the probability of attachment depends on time. Okay, if you arrive at time I, then the probability that you attach to time j to vertex j now depends on the time that passed between I and j. Okay, we call this a subtractive attachment mechanism. Nothing is known about this. We've been analyzing this type of trees, but not the archeology problems. Geometric trees are obviously a nice extension of this. So in geometric trees we have vertices correspond to points, let's say in the plane or in some other space. So they are random. So vertex number 1 comes, it's a point. Vertex number 2 attaches to it. when vertex number 3 comes, it attaches to the nearest one. This is the online nearest neighbor tree. Okay? So randomness is now in the vertices, not in the edges. Okay? And now you grow this tree. So there's a recent very nice paper by Liuben Lichev and Dieter Mitsche where they analyze this kind of online nearest neighbor trees. They have lots of very nice properties. This is substantially more difficult to analyze the properties of these trees, and as far as I know, nothing is known about the archaeology, finding Adam in this kind of trees. There are all kinds of hybrid models that combine geometry and preferential attachment. There are a few references here. A different kind of problem is, can you estimate the underlying dimension? This is not about archaeology, but if you observe, let's say, a geometric, let's say an online nearest neighbor tree, but you don't know which space it came from. You just know that it's an online nearest neighbor tree in some space. Can you tell me something about the structure of that space? For example, the dimension. Okay, can you estimate the dimension? That's a nice statistical problem. Now, recently with Simon, who's sitting here, and Francisco Calvillo, we extended this. This is not written up yet, but I'm confident that it's correct. Everything that I told you so far is about trees. And the tree structure is very important because we look at these centrality measures. That as soon as you have even just a few edges added to the tree, then all the centrality measures are now become. How do you compute this? How do you know which one is central when you have these shortcuts? Okay? So what we analyzed was the so-called Cooper-Friese model. So they came up with a model which is a preferential. They formulate it in a very general manner, but the simplest way is the following. So vertices come one by one, and then when a new vertex comes, at the next time, two things can happen, and we flip a coin to decide what. So we flip a coin. If it comes up heads, then we add a new vertex, and let's say attach uniformly. Okay. And if it comes up tails, then we don't add the new vertex, but we add a new edge at random, okay, to the existing ones. So that's the Cooper-Friese model. Okay? So it's a nice, nice model where you have something much more complicated than a tree, and all these centrality-based methods stop working. Okay? So in this particular model, we proved that it is possible to find Adam in the sense that the problem doesn't become harder so again, that K is just the number of vertices that we have to output is only a function of epsilon. We have some really bad. I think we get something like log 1 over epsilon factorial or something like that, right? Which is surely not optimal, but we can do something. Okay? And you can imagine many other models of trees that may be more realistic than this one, though Cooper and Friese insisted that this was a realistic model, and try to do real network archaeology, not just tree archaeology. Okay? And there are other models, again, community modulated recursive trees that were introduced by Shankar Bhamidi, Nicholas Freiman, and Andrew Noble, where the vertices that come have a random color, and then who they attach to depends on their color and the color of the other vertices. Okay? So if a red vertex will be, let's say, more likely to attach to red vertices than to blue vertices. So this is what we call the community modulated recursive trees, also very nice model. Yeah, and there are many other things that you can play with. And that's all I wanted to say today.
Okay.